All right, I want to introduce a concept which was not in the book, which you might come across in your outside studies, possibly. I don't think that they're on the SAT Chem, but it's good to know. These are called ICE tables, ICE. These are basically used for questions like this when you have an equilibrium, which is they give you initial concentration and they're asking you to find equilibrium concentrations. ICE stands for initial, change, and equilibrium. So there's a neat little table that you can set up called an ICE table, which you see here. Okay, so first thing you want to do, obviously read the question. So consider the reaction for the decomposition of hydrogen iodine at 448 degrees C. The initial concentration of HI was 1 millimole per liter. Once an equilibrium was established, the concentration of HI was measured to be 0.078 millimoles per liter. Calculate the equilibrium constant. Okay, so what you want to do first is set up your ICE table. So let me go ahead and erase that. Okay, so actually before we set up the ICE table, we need to have our chemical equation. Geez, it's long. So we have 2HI, and we've got a reversible reaction. We have H2, it's a gas because decomposition. And if you remember from last year, probably not, but decomposition of a binary compound, which is a compound with only 2 elements, they decompose into their elements, which is hydrogen and iodine, both of which are diatomic. Okay, now on the left-hand side, you put I, C, and E. Okay, now here's where it gets interesting because I is initial concentration. So according to the question, the initial concentration of HI is 1. So I'm going to put a 1.00 here. And you don't know the initial concentrations of hydrogen and iodine because they're not given in the problem. But if you use your thinking meat, you understand that initially there are no products because the reaction just started. So the initial concentrations of hydrogen and iodine gas are 0 because initially there are no products. Now, C is the change in concentration. Here's where we're going to get a little bit algebra-y. Algebraically, algebra-y, yeah. We're going to be algebra-like. So the amount that hydrogen iodide gas is changing is dependent on its coefficient in the equation. So I'm going to call this minus 2x. So x is the amount of concentration that's changing, and whatever that is going to be 2, because from the balanced equation, it's 2 hydrogen iodide. Now, the amount that hydrogen and iodine are going to change are going to be plus x each, because you're going to be producing 1 time because of the balanced equation. So if I try to clear this up, if it's confusing so far, basically, if I have, I should have a laser on this thing. If I have 2 molecules of HI, I'm going to lose 2 molecules of HI, and I'm going to produce 1 molecule of hydrogen and 1 molecule of iodine. So you're going to think of it that way. And that's your change. Now, the equilibrium concentration is going to be the initial minus, sorry, the initial plus the change. Because whatever you start with, plus however it's changing, that's what you have at equilibrium. So that means 0 plus x, that's x, and x here. Now what I can do is write my equilibrium expression. I guess in this case they want it in Kc. Oh, because they want the equilibrium constant. Okay. So my expression is H2 times I2. Remember, products over reactants raised to the power of their coefficient. Okay, and now I'm just going to put in my equilibrium concentrations here. So that's x times x over 1 minus 2x squared. So that's equal to x squared over 1 minus 2x squared. So then you might think, okay, how does that help? Well, we go back up to the question. Once an equilibrium was established, the concentration of HI was measured to be 0.078. Okay. So the concentration of HI at equilibrium is equal to 1 minus 2x, right? So we've established it here. But now we can put a number on that, 0.078, according to our question. So now it's a matter of doing your algebra. So that's 1 minus 0.078 is equal to 2x. This is 0.922. 2x. X is equal to 0.461. Okay, so now I found my value for x, which I can put up here back in my equation. So equilibrium constant is equal to, now both the numerators, x squared, 0.461 squared, over 0.078 squared, which is 34 point, well, that would be nice if I wrote the right number, 34.93. Ta-da!